This is the review for the Chapter 2 test on 2.1 to 2.5. You should write this out on a blank sheet of paper and then it'll get stapled to your list of things that need to be completed to be eligible to get some test points back in the event that you need them. So, I don't have any 2.1 on here because that was our definition of the derivative using the limit process. I'm not going to actually test you on that process. I will have you recognize it in one multiple choice question, but mainly the test is on 2.2 to 2.5. So in 2.2, and again you should write this down, so you might need to pause too because I'm going to go kind of fast through it, but these are the basic rules for finding the derivative, and I'm purposely mixing up the notation on some of these so you get used to using d dx, f prime, y prime, etc. So our first rule was the constant rule, which said that the derivative of any constant is 0. That one was very easy. Then we had the power rule, and this one we use a lot. That said when you take the derivative of x to some power, the power comes out front and you knock it down a degree. Be careful again when you're using, let's say, rational exponents, and you bring that out front, and then you subtract 1 from it, and you get that negative 2/3. Kind of be careful how you write that final answer. When that's all said and done, because x is to a negative power, remember that goes down to the positive power, so that'd be x to the 2/3 on the bottom, and then remember that this right here means the cubed root of x squared, so we'd write that as 1/3 times the cubed root of x squared. So I'm pretty comfortable cleaning those up, but other than that, the power rule is very straightforward. And then we had the property that said the derivative of a sum is the sum of the derivatives. Likewise, the derivative of a difference is the difference of the derivatives. Very straightforward. Notice that we don't have one for product and quotient because it doesn't work. We have special rules for those, which are coming up later. And in 2.2, we started with our derivatives of the trig functions. And our first one was that the derivative of sine is cosine. And then we had the derivative of cosine is negative sine. Those need to get memorized. So combining a couple of those in one, if your function was, say, y equals 2 sine x plus cosine x, this would be, when I find the derivative, I have the constant multiple rule right here, so that doesn't affect anything. The derivative of sine is cosine, and the derivative of cosine is negative sine. So I just kind of used a constant multiple rule. I used the derivative of sine, the derivative of cosine, and I used the sum rule. So very straightforward in that section. We also talked about the average rate of change being the slope of the secant line. So remember what that meant, that if we had some curve here going like this, and we want the average rate of change maybe between these 2 points, then we find the slope of that secant line. The instantaneous rate of change is the derivative or the slope of the tangent line, but the average rate of change is the slope of the secant line. So that's just change in y over change in x. And then on the bottom I wrote that for over an interval where it says, remember, this is the slope of the secant line, or if we're looking at it over a comma, let's go put that on here, b, where this would be the point a comma f of a, and this would be the point b comma f of b. Then when I'm looking for that average rate of change or the slope of the secant line, I'm still doing change in y, but it looks like f of b minus f of a, change in y values, over change in x values. Okay? And that would be called the average rate of change. Remember, the derivative is the instantaneous rate of change. So moving on to the next page here. We've got some more rules for finding the derivatives. The next we had our product rule, which said that when you're doing the derivative of the product, and again, we did it first times the derivative of the second plus second times the derivative of the first, but because addition and multiplication are commutative, it really doesn't matter. So you can jumble those up however you want. I would stick with this one because that's what we've been working with. The quotient rule for finding the derivative of a quotient is, remember, low, d high, minus high, D low, draw a line, and square below. And you should memorize that, but we've been using it enough where I think it's pretty straightforward. Then we went and we dealt with the next 4 of our trig relationships, and these need to get memorized. There is a pattern to them. I proved this one in class. They all get proved using the quotient rule, to be honest with you, so you could go prove them all if you wanted to, but if you want to look in your notes for the proof of that one, you could. The derivative of tangent is secant squared. Cotangent is, again, reciprocal function, so we do reciprocal, and it goes negative. And these just need to get memorized. So you can write those down, and maybe you already have them memorized. But I would suggest writing all 6 of them, including your derivative of sine is cosine, and your derivative of cosine is negative sine. And part of the retake is writing those out a couple times. You have to look at your sheet for that. After we dealt with those, we went into what we call the chain rule, which is how you take the derivative of a composition of functions. And this part really is when I talked to you about how, suppose we had f of x equals, and we had a composition of functions. Sorry, I had to pause the recording there. Someone came to the door. So anyway, back to this. Suppose you had a composition of functions. So I've got this linear function, and I'm going to say cube it. In all this notation, this would be considered u, or the book sometimes calls it g of x. And remember I told you that you take its derivative with respect to u, which would be 3u squared using the power rule. And then you take the derivative of that inside as it is, which we call u prime, or you could call it du dx. So really what you're doing is you're taking the derivative of that function, you can call it y or f of x with respect to u, times the inside with respect to x. And you can kind of consider those canceling. They don't, but it kind of helps you keep the chain in line. So it's explained this way with the dy dx function. It's also explained with the f of x, g of x notation here also. But basically what it's saying is you take the derivative of the inside, and then you take the derivative of the guts. So let's try one off to the side here just to make sure you have it. I think I'll put it in with the trig notation. So let's suppose you had y equal 3 sine cubed, and let's even make it a multiple chain rule and write it like that. This would be just the constant hanging out front, so I'd use my constant multiple rule. I also told you that when you have like the powers of the trig functions, it is actually helpful to rewrite that with the cubing outside. It helps you keep in line how the chain is supposed to get done. So I have 3 functions really going on here. I have a cubing function, a sine function, and a linear function inside of it. So when I use my chain rule on that, I've got my constant multiple up front. And again, the book says, if you consider this u, it'd be 3u squared. Well, that's what I need to do. I need to do 3 of sine 4x minus 1 squared, which is going to come in here like this. And then I do the derivative of the next one in the chain, which is sine. And the derivative of sine is cosine. So I'd say, well, that's cosine 4x minus 1. And then I do the derivative of the innermost function, which is 4. And then, of course, you'd clean that all up. I think you'd end up leading with a 9 times 4, etc. So you would be able to work your way on through that. Next page, just about done here. Then we talked about how when you take the derivative of all these trigonometric functions, and you're doing it with a composition, and that's just what I did on the last page. I'll just throw one up here. Suppose you were doing, just so you get what this is saying, suppose you were doing the derivative of, let's say, y equals tangent 4x plus 3. Again, this would be considered u in this scenario. So you just do secant squared u, so I do secant squared 4x plus 3 times the derivative of u, which would be times 4. And it'd come out front. So very straightforward with those. And then last up we did our implicit differentiation. And remember, you need to know and have this process down. We did enough of them where I think you're probably pretty comfortable with it. But we use the implicit differentiation when x and y are on the same side of the equation. When it's not written like just f of x equals or just y equals, where we actually have maybe x squared plus 3x squared y equals x plus 1. Something like this is where we use our implicit differentiation. And remember, first thing we do is we differentiate both sides of the equation with respect to x. Then we collect all terms involving y prime on the left side of the equation and move all other terms to the right side. Remember, in this step right here when you're differentiating, watch out for that chain rule. For example, if it was, say, x plus 3xy squared equals 4, and you take the derivative of both sides of that with respect to x. Derivative of a constant is 0. Remember on this side, since I'm doing the derivative with respect to x, that's just the derivative of x, which is 1. But on the next one, I'd have the derivative of a product. And again, the constant multiple rule would come into effect. I'd pull the 3 out. But I'm going to have to do the product rule on here. And remember, when you do that, because you're doing it with respect to x, in the process of your product rule, when you do the derivative of y squared, remember when there's not a match here, we consider y a function in and of itself. So we take the derivative to y, and then we multiply it by the derivative of y. So in the process of the implicit, watch out for your chain rule. And then remember, the rest of this was pure algebra, some factoring and some solving. So last step that I want to talk to you about is the relationship between position, velocity, and acceleration. And all of these are done with time being my independent variable. And remember, velocity is change in position over change in time. And it's the derivative of the position function. So remember that. If I'm asking you for velocity, you need to do the derivative of position. So for example, if the position function was, say, 4t squared plus 2t plus 1, then my velocity is the rate of change of position over time. So it's the derivative of position, which would be 8t plus 2. Likewise, acceleration is the derivative of velocity, or the change in velocity over time. So if now I wanted to know, sorry, that would just be v of t. If now I wanted to know my acceleration, I take the derivative of velocity, or I could even consider it the second derivative of position, and that would just be 8. So, that's about it for this part of the review. You should have all that written down on a separate sheet of paper, and if you have any questions about it, you should ask me. See you later, guys.